Resonance is very important concept of this GOC. Not only GOC, it is the core, it is the heart of organic chemistry. So today we will discuss the resonance, right? First you have to understand that what is resonance. A resonance is the delocalization of pi electrons. A resonance is delocalization of pi electrons. I write here this simplest definition: delocalization of pi electrons. But you may find it difficult to digest. You may find it difficult to understand this statement. You have seen different kind of definition of resonance in the first year in the chemical bonding chapter. There in chemical bonding also resonance topic is there, that is very limited. In there you have learned that resonance is the phenomena of representing the same molecule in the different electronic forms. Understand what I am telling you? This is resonance is the phenomena of expressing the same molecule in many other electronic forms. All those electronic forms represent the same molecule. All those different electronic forms, when I say different electronic forms, means only the arrangement of electrons is different in only the arrangement of electrons is different over there. Understand? Here you know one very good example, and I would like to take your example for your better understanding. I just take one example of CO3 2 minus carbonate. Here there is double bond in between this carbon, that oxygen, there negative charge, here negative charge, but there is other way of writing that this double bond we can write here, and this oxygen and that oxygen will have the negative charge. This one is like this. Again, there is other way that this will be here, this will be there. It means here these two, this will be having double bond and these two will be having the negative charge. There double bond, here negative charge, and here negative charge. This kind of example on the name of resonance, and how it is resonance that you see that the same carbonate is represented, expressed in this form also, that form also, that form also. You can say, sir, all these forms are same, but understand these all are not same, because in this case this oxygen is having double bond, in this case this oxygen, and in third one that oxygen, means this pi bond keep on changing its place. Pi bond keeps on changing its place. This thing we are getting This thing we are getting from this one. So this is the point here. This way of expressing the same molecule is called resonance. Then you can ask me, sir, what is the point of this definition, delocalization of pi electrons? The delocalization of pi electrons is not different from this definition, where we say a resonance is the phenomena to express the same molecule in different electronic forms. It's not different. How it is not different? Let's understand here delocalization of pi electrons. First you have to understand here the pi electrons. What are pi electrons? Pi electrons are those electrons which are present in the pi bond. This is correct. If you answer like this, this is correct, but this is not 100% correct. It's a partial answer. It's not complete answer, right? What are the pi electrons that you understand? The pi electrons means electrons present in unhybridized orbitals. Electrons present in unhybridized orbitals. Okay. Pi electrons is that. Unhybridized, you know. Hybridized and unhybridized. Here, how your definition will be justified? Because you say electrons present in pi bonds. Yes. Which orbitals form pi bond? Do you remember? Recall this part. Which orbitals form pi bond? Only unhybridized orbitals form pi bonds. Hybridized orbitals always form sigma bonds. Unhybridized orbitals only undergo lateral overlapping, form their pi bond. Okay. So then your point is correct. But why I have written? Because you may have another situation where electrons are present in unhybridized orbitals but not forming pi bond. Understand? That time how you count pi electrons, that is very important one. This only example you take. Here 2 to 4 we take here. Here also we take. Now I am telling you, as per your concept, as per your perception, how many pi electrons are present in this one? 2. How many pi electrons are present? Only 2. Where is that? The pi bond is there. There, sir. But I will say here there are the 6 pi electrons. There are 6 pi electrons. Certainly here we have one sigma, one pi, one pair of electrons sigma, one pair of electrons in pi, so 2 electrons here. And the negative charge, what we say, which is capable to move, that is also present in the unhybridized orbital and pi electrons only. I am giving another good example. Okay, you will understand this one. When we write here the CH3, CH2, CH2 minus, we try to know the hybridization. Understand, listen this concept very carefully. When we write like this, CH3, CH2, CH2 minus, the negative charge here present, and what is the hybridization of this carbon atom? Its hybridization, you will say, sp3. 3 bond pairs, 1 Cc, 2 Ch, and 1 lone pair of electrons in the form of negative charge. So total 4 electron pairs, 3 bond pairs, 1 lone pair. Here we get negative, so its hybridization is sp3. Fine. Now I change here the situation. I write here CH2 double bond CH, and here the CH2 minus. Here we have CH2 minus. There we have CH2 minus. Here I say the hybridization is sp3. What is its hybridization? Its hybridization is not sp3. Its hybridization is sp2. Whatever rules you have learned to predict hybridization will not help you to predict the hybridization of this carbon atom. It's conceptual. It's conceptual. Here you have to understand that why its hybridization is sp2. Its hybridization is sp2 because there are only 3 hybridized orbitals. Which are those 3? One Cc and other Ch, other Ch. What about this electron pair negative charge? That is present in unhybridized pure p orbital. That is not participating in hybridization. Then you can ask, why it is not participating? It is not participating because it assumes greater stability when it moves. It interacts with this one. So as if this is sp3, then this cannot move. If it is sp2, then it can move. And if it is moving, then there it will be having greater stability. So it prefers to move here. Then you can ask another question, how it can move, sir? Because it can move because its hybridization is sp2 only. And there is one unhybridized pure p orbital, one unhybridized pure p orbital is there. That's why that orbital can entertain its movement, can interact with this one, can accept this pair of electrons, will form here one pi bond. There is possibility of formation of pi bond because one pi orbital is already present there. This can facilitate. Then you can ask me one question. Sir, if that is the case, then why this is not moving? This won't move because there is no scope of its movement. Why there is no scope of movement? Because this carbon is sp3. It has no any such unhybridized orbital to interact. Here all are sigma bond. There is no possibility, there no interaction, that's why it is not possible. But in this case, as the adjacent carbon atom, adjacent atom is available, for interaction, for the formation of another pi bond with one pi orbital, unhybridized orbital. That's why it prefers to change its hybridization and it is sp2. Sir, then is it possible in any other cases? It is possible in all such cases. Whenever you find the lone pair, whenever you find the negative charge present on an atom and on the adjacent atom, if the hybridization is sp2 or sp, then its hybridization will be sp2 only. Suppose I take this one and their adjacent one is sp2, so you just consider hybridization sp2, right? If adjacent one is having sp3, then this negative charge will be having hybridization sp3 only. This way hybridization is optional for these atoms. I hope you got it. And I will be giving you more and more example. More and more example. Darun, that is also correct, as it can form double bond, what I am talking, that's why also you can say sp2. That is very nice interpretation, right? As it can form sp2, form pi bond, that's why also you can say. So that thing you have to understand, where it can form double bond, right? Very nice. Exactly, I am giving another example. You take this example, it's very known example, NH. What is the hybridization of this nitrogen? Ahmed, what is the hybridization of this nitrogen? Hybridization of this nitrogen is sp3. Here NH, NC, NC in one lone pair, so its hybridization is sp3. Correct? Now I am taking another example. Here no negative charge. What is the hybridization of this nitrogen? Pranav, concentrate now, okay? Will be available later also. First you concentrate here. So, understand this one. What's the hybridization of this one? Rachit, very good. Its hybridization is sp2. You know why? Because, very good, very good. Because this can move. And why it can move and can form here double bond. How it can? Because this will be here. This bond will break down and we can have this kind of structure where we will write like this and their negative charge and this will be like this. So there is a possibility of this kind. It is happening. And that's why we say, assuming this kind of phenomena, assuming this kind of possibility, we say its hybridization is perfectly sp2. Its hybridization is sp3. Very good. I feel you understood this one very well, right? So this is the way we identified pi electrons. If I ask one question, how many pi electrons it has? 0 pi electrons. How many pi electrons it has? 0 pi electrons. Number of pi electrons, let's discuss your question. Number of pi electrons you have to answer. Here CH2 double bond, there the CH2 minus. Number of pi electrons here CH2 double bond, there the CH minus, CH2 minus, pi electrons here, NH, number of pi electrons here, number of pi electrons here, number of pi electrons here. This is the first one, second one, third one, fourth one, and fifth one. Number of pi electrons in these 5. In first case, how many pi electrons? In the first case, how many pi electrons? Good. In the first one, pi electrons only here, 2. This negative charge, this electron pair is no more considered pi electrons. Clear? Because adjacent one is sp3. There is no interaction, no pi bond formation. That's why this is sp3, this one sp2, this one sp2, this pi bond, 2 electrons. That's it. Very good. Here the pi electrons, 2. What about this one, second one? Second one pi electrons, how many? This one, there is negative charge, adjacent one is sp2, and certainly there are the 2 electrons, 2 pi electrons, and there 2 pi electrons, total pi electrons is equal to 4. Very good. Third case, how many pi electrons? Third, how many pi electrons? When you write answer, you should write 3. There the 2, 4. Like that you should write. Otherwise there I will be confused. For which one you are saying 3 or 4? Right? Yes. But third, your answer is wrong. Because in this case, again this lone pair is there, and adjacent one is sp3. So this one is sp3 hybridized. This one is sp3 hybridized, this one sp3. Here we have the pi bond, so only 2. In third one, how many pi electrons? Only 2. Because the nitrogen containing pair of electron is present in hybridized orbital, not in unhybridized orbital, right? Fourth one, how many pi electrons? Fourth one, how many pi electrons? Very good. 4, 0. In this case, no pi electrons. In this case, how many pi electrons? Fifth one. Very good. Fifth one, 6. 2 to 4 to 6. Perfect. Nice. Good answer. So one thing we have learnt, pi electrons means electrons present in unhybridized orbitals. So now you can justify it very well that in this case, how many pi, in carbonate, how many pi electrons are there. So as this can form here, double bond, this can move, so this is also pi, this can move, that is also pi, this one is pi, total 6 pi electrons. Correct. Now I will discuss here the other part of this definition, that delocalization of pi electrons. You learned pi electrons. Nice, I am very happy. What do you mean by delocalization? Delocalization, when something is localized. Here localized, when I say, understand the meaning of the localization, that if something has one more identity and that is the location. If location is also one of the identity of that one, that is called localized. If the location is not fixed, location keeps on changing. Location cannot be the part of identity, cannot be one of the identity, then that is called delocalized. There in the class itself, when you are sitting 3-4 students, and always if you are sitting on the first bench in the middle row, then your teacher is having one impression other than your name. Yes, one fellow in the middle row of the class on the first bench, you are just creating one more impression, one more identity, and you are localized. But at the same time, when some of the fellow in the class sitting one day on the front bench, other day, other bench, third day, third bench, fourth day, other bench, keep on changing the place, then the teacher is not getting connected with him so well and so precisely. That fellow is delocalized. When that fellow is changing its place, means delocalized. Same thing here, the electrons are localized, electrons are delocalized. If the electrons keep on changing the place, we say delocalized, right? So delocalization of pi electrons. But for that, for the delocalization, there should be some space, there should be some possibility, or not? Here there is negative charge. Is it delocalized? No, it is localized, because this cannot change its place. Here you see this electron pair will be localized or delocalized? Will be delocalized. At present this electron pair is here, but can change its place, will form double bond and can come to this place. So that will be delocalized. But here localized, here delocalized, can keep on changing its place, right? So now you will be very clear with this definition, delocalization of pi electrons, and why we say resonance is the phenomena to express the various structures for the same, various electronic structures for the same molecule. Because in the resonance, again I come to this point, again and again I am telling you this one, and you focus on this one, that I am telling you they are the different electronic arrangement. Localization, delocalization, I am not telling you here the different arrangement of atoms. Atoms are not changing their places. Atoms are not changing. I am not talking about the change in the arrangement of atoms. No. Change in arrangement of atoms leads to isomers. You are getting isomers. But change in arrangement of electrons leads to resonance, and resultant structures are called resonating structures. Resultant structures are called resonating structures. I hope you got it. So here, where you will get resonance? Is there any condition for the delocalization or not? So for that, here types of resonance I write. Resonance types, there the first one, delocalization of pi bonded electrons with pi bond in conjugation. Conjugation means the alternate arrangement of bond. Conjugation, one next, one after one. This is conjugation, alternate arrangement. Delocalization of pi bonded electrons with pi bond in conjugation. CH2 double bond there, the CH in there, the CH double bond CH2. This one is, I say, delocalization here. This is a conjugated system. Double bond is there, pi bond is there, again leaving one, again pi bond. This is the conjugated system. Here pi bonded electrons undergo delocalization with the other pi bond. How we break this one? We write, you see, arrow is also very important. What is the meaning of this arrow? Meaning of this arrow is this pi bond breaks down. Meaning of this arrow is this pi bond breaks down. In pi bonded electrons, both electrons of this pi bond will be there now on this carbon atom only. In this one electron is contributed by this carbon, other electron is contributed by this carbon atom. So when both the electrons will come here, you will write here the resultant structure like CH2 double bond CH, and there the CH, and here the CH2 minus. Understand, I am going to discuss here even minute detail. I need your attention. I say that in this pi bond, two electrons are there, one of this carbon, another of this carbon atom, and pi bond breaks down and both electrons will be accumulating on this carbon atom. We write negative charge. Negative charge means how many electrons are there? Negative charge always represents here, unit negative charge means how many electrons? 2 electrons. How many extra electron? 1 extra electron. That's why unit negative charge. Because both are accumulating here, but one thing you understand, that only 1 extra electron of this carbon atom has been taken by this carbon atom. That's why we say unit negative charge. And as this carbon atom has lost one of its electron, so this will be having positive charge. It means this orbital is vacant. Earlier how the bond was there? This was the pi bond here. This pi bond was there like this. This was the pi bond. Now there is no pi bond because here the electrons are taken now and both electrons are here now. Now both electrons are here. Then the negative, this orbital is vacant. This orbital is vacant. Exactly. That's why we have it in the positive charge. This is ready now. Here positive, this is vacant now, there is negative charge. Now this is the vacant, so this can also accept electron and can form the pi bond. So what is happening here, this carbon is taking both the electrons and giving to this one, right? So when this carbon, again there the 2 electrons are there in this one, in this pi bond. 1 electron of this carbon, 1 electron of that one. So taking this electron, both the electrons, this one is taking both the electrons. So this carbon will be having 2 electrons. And with the both electrons, this orbital will be shared and will go there. We express this one like this. It is spreaded in between these two, and for that this orbital is taken, right? Now what will happen there? This carbon is left with no electron now, CH2 plus, because its orbital is vacant. This orbital will be shared now. So CH2 and there the CH double bond there, the CH and CH2 minus. You understand that how it forms, how electrons move. It was there the CH2 double bond CH in there, the CH double bond CH2 we have written like this. Again this one like this. Electrons move, changing its place. In this case pi bond is here, now the pi bond is there. It is delocalized. Correct or not? This is called delocalization. Here delocalization is possible. Here this delocalization is possible because pi bonds are there in conjugation. This is the way you will break one pi bond. You will write there negative, you will write there the positive, and then the other bonds will follow that one. And this kind of thing is happening. Here same thing, you can write CH2 double bond there, the CH. Otherwise you take the better example, more prevailing example, benzene you take. This is benzene. What happens in this case? Audio is there. You break it, we break it. What I should write? I take this one is 1, this one 2, this one 3, this one 4, this one 5 and 6. We break the bond in between the 1 and 2. Ajay, once check it. Ajay, any problem with the audio? So in this case we break one pi bond. When we break here the pi bond in between 1 and 2, then what we write? We write negative charge on the first and we write positive charge on the second one. Their negative charge let remaining as it is and their positive charge. What we'll do now? What we'll do now that there, this one is 1, this one 2, this one 3, this one 4, 5 and 6. What's the next one? We'll break now there the pi bond in between there the 3 and 4. There the 3 will be having negative and 4 will be having positive, and so this negative will be given there. We don't write these many in detail. Directly we indicate that the bonded pair of electrons now shift in between 2 and 3. Why this shifting is possible? This shifting is possible because there the second place, one of the orbital is vacant. So what I mean to say, what is the resultant structure? Resultant structure is like this. Their negative charge, so the positive charge comes on this 4th place, 5th place and the 6th place is there like this. Next you see what we will do. We will break here the 5 and 6 and that bond between the 5 and 6 will be moving towards the 4 because the 4th one is having the vacant orbital. So that is moving. And how to indicate that? You see, it must be indicated in the middle of the bond. When we show there the shifting, it means in the middle of that. Accumulation means exactly on the same carbon atom. Just give some in the chat, you write some instruction, okay? You write there, refresh it or something because he is just finding difficult. So what is the resultant one? Resultant one is now there is bond, their negative charge, and now the positive charge comes to this 6th place. 6th place positive charge. This is the first one, and a first one negative charge in there, the 6th one positive charge. What next? Next is negative charge is there, positive charge is there, it means here is the vacant orbital, there one of the orbital is present with the 2 electrons. So this can interact with this one and new bond will form. This one, this one, this one. Correct. You see there this structure and this structure. This is also benzene and this is also the benzene. We say these structures as resonating structures. We say these structures canonical structures. Here you understand that you have written like this, you have written like this. In this case there is double bond in between 1 and 2. In this case there is single bond in between 1 and 2. What we say this one? Delocalization. It is not fixed at one place. It is changing in its place. The pi bond which was there in between 1 and 2 is now in between 2 and 3. Which was there in between 2 and 3, that is now in between 3 and 4. Changing its place and keep on changing its place. There is the continuous delocalization because there is a scope, and how there is a scope, that is very clear in this case. These are the intermediate canonical structures. These are the resultant canonical structures. These are resonating structures. What we say? Resonating structures. We also say canonical structures. Okay. Means in the resonance, when you express one of the molecule in the various forms, in the various electronic arrangements, those various electronic arrangements are called resonating structures, canonical structures. I hope you got it. If there is no vacant orbitals, then there is no resonance. That only we explained now. In this case, you see no vacant orbital, no resonance. You cannot expect a resonance in that case where you don't have the vacant orbitals or something. We have, this is one class of delocalization. I am going to discuss another class of delocalization. Delocalization of pi bonded electrons with pi bond in conjugation. This is one. Just you wait for the other class, other type basically. I am going to discuss here second one, delocalization of pi bonded electrons with unhybridized orbital. You know the meaning? Unhybridized orbital, what we say? We say pi orbital with no electrons. In this case also you can have delocalization. Delocalization of pi bonded electrons with unhybridized orbitals means pi orbitals with no electrons. You may have this kind of situation for the delocalization. One example you take CH2 double bond, there the CH and there the CH2 plus. What is the hybridization of CH2 plus? Hybridization of the CH2 plus is sp2. This one is sp2, its hybridization is sp2. When we say sp2, it means there is one unhybridized orbital here. And when we say plus, it means that is vacant. When we say plus, then that is vacant. So in this vacant orbital, here bonded pair of electrons can go. I have written this bonded, the movement of this pi bond in between these two atoms. It is not simply given to that positive. it is there in between these two, it means now there will be sharing in between this and that. In the resultant one, we write here the CH2 plus. Now this carbon will be having one of the orbital with no electrons, because this carbon has taken those electrons from this one, so this is left with one of the orbital with no electrons. So CH2 plus, and there the CH double bond CH2. Okay. Now you see, now again you can reverse. This can be very long one also. I am discussing here one more, right? Third one, you see there is a third one. How the video will be repeating, right now it's live. Maybe there when you are refreshing, there is some time lagging is there. So you should not worry. You can refer, if you find it bit inconvenient, you can refer this lecture again, because this will be uploaded. In that time there will be continuous movement, right now. So no need to worry. What is there? Please concentrate on this. Third one, delocalization of pi bonded electrons with pi orbital with 2 electrons. Understand? I am giving you all possible options. All possible options. You cannot have any example more than that, right? I am going to take here the 4, and the complete resonance of the organic chemistry will come under these 4 categories, right? So this is third one, delocalization of pi bonded electrons with pi orbital with 2 electrons. Pi orbital already I told you, unhybridized orbital. So CH2 double bond there, the CH2 minus. We discussed a lot. This will help you a lot. Its hybridization is sp2. Today only we discussed. So this electron pair is there in, this is also pi electrons. Now the pi electrons will be moving towards. How it can move towards? Yes, because this is also sp2. This has one of the unhybridized orbital. But then you will ask, why sir? That is already occupied. Not a problem. That is already occupied, that is already having bond with the other carbon atom, not a problem. If that is giving, then this carbon will advise that you take this pi electron pairs. Will like this. I am taking from this one, so you take mine. Will be pushed there, then there will be negative charge. So this one is ready now to accept electrons. So the resultant one is now CH2 minus CH double bond CH2. There is no pi electrons, no negative charge here, because that electron pair is now in the form of pi bond here in between these two. And what about this one? This was forming one pi bond with this one, given its own electron also. to another carbon atom that you take, and so this one is having negative charge. This is also one of the way of delocalization. In this case, negative charge is moving. So to express this kind of delocalization, we have to use the two arrows simultaneously. It is not like the positive, where the single arrow is enough, two arrows, because we have to express that how there the next place is available for delocalization. I am just taking the bigger system of this one. I take the bigger system, CH2 double bond CH, in there the CH double bond CH, and here the CH2 minus. Bigger system. In this case, this electron pair is coming in between these two. I say this is 1, this one 2, this one 3, this one 4, this one 5. What will you write now? You will write here the CH2 double bond CH without any change, and this will be having, as this is coming here, so pi bond will be there in between 1 and 2. But how is that possible in this present condition? Because then this carbon will be having pi bonds. So this carbon is losing this one. So this third carbon will be having non-negative charge. So now this second carbon atom is ready to form pi bond with this first one. Yes, it is ready now. This third carbon atom is now again giving its electrons to this fourth one. How it will be giving? For that the fourth has to be ready. And how it will be ready? By giving its pair of electrons to the fifth one. Now you keep this one. I am taking from this one. So the resultant structure you will be getting here the CH2 minus, and now there double bond in between the fourth one and third one, and the second one and there the first one. This is the way delocalization is going on. Are you talking this problem? This third case or the second case? May try any. Which case? This third one or second one? Third one. Okay. Third one, negative charge is present here. Means this orbital is having 2 electrons. This orbital is having 2 electrons. So, and its hybridization is sp2. This is unhybridized orbital as we discussed earlier, because the adjacent one is sp2. So, with this electron pair, this carbon can form a new pi bond with this carbon only if this carbon will be losing its own pi bond with that carbon. So, it is happening. This carbon atom, this adjacent carbon atom is taking this electron pair with this carbon and losing this pi bond to that one. So, this another carbon is taking this pi bond and forming negative charge. Negative charge means bonded pair of electrons accumulate over there, that is why negative charge. In this one, 2 electrons are there and one is there of the same carbon atom, and 1 electron from this carbon it is taking. So, it is non-negative charge that gets accumulated over this one. This is the way it accepts. This is the way here the electrons move. Here also the same thing, this electron will be moving, pi bond will form, but for that it has to lose. So very first we write negative charge here. We have written negative charge, there pi bond. Now again this negative charge can go further. We'll form here the pi bond, then for that this will be moving there. So you express all this. These are various electronic arrangements for the same molecule, right? These are called, as I said, resonating structures, canonical structures, right? So fourth one also you take, one more situation we have there, the delocalization of pi bonded electrons with pi orbital with one electron only. Yes. Is it possible with one electron? Yes, it is possible with one electron also. CH2 double bond, there the CH and there the CH2. This carbon is present with one electron. We say this space is free radical. What we say? Free radical. Free radical. What is its hybridization? sp2. Hybridization is sp2. What is the meaning of sp2? There is one unhybridized orbital which contains one unpaired electron. Okay. This is unhybridized, unpaired. So now in this case, as this is unpaired, so this can accommodate only one electron. Here there is no movement of two electrons. There is movement of only one electron. It cannot take two electrons. So here this adjacent carbon atom is coming with only one electron towards this one. Half arrow, half-headed arrow. This is the movement of one electron. So this carbon, when going to this carbon atom with one electron, then what will happen there? This carbon is coming with one electron. This is having one electron. So one pi bond will form. Then what about this carbon? This carbon is left with its own electron, unpaired electron. So what is the resultant species? CH2. This electron is left. And what about this carbon? It has utilized its own carbon atom this side with this one. So now this electron pair is already here. This what has been taken, that is there. Okay, bond formed. And now we find that electron is there. Different electronic arrangements. This is 1, this one 2, this one 3. In this case we observe there is double bond in between 2 and 3. Now there is double bond in between 1 and 2. This is called delocalization. I am telling you, you cannot have any more example. You cannot have any more example of the delocalization. We have delocalization in these 4 categories only. Delocalization of pi bond with pi bond, delocalization of pi bond with carbocation, with one of the unhybridized orbital, pi orbital with no electrons. No electrons means carbocation we say. Delocalization of pi bonded electrons with one of the pi orbital with 2 electrons, carbanion, that is a negative charge, it is there. And delocalization of pi bonded electrons with pi orbital with 1 electrons, free radicals, 4 categories. Okay. So this is the point here, that let's take here the benzene, and I explained that this is one of the canonical structure of benzene. One of the canonical structure of the benzene, one of the resonating structure of the benzene. And what is the other one? This is moving here, that is moving there, and we write the another one, double bond here, double bond there, double bond. This is the another canonical structure of the benzene. A benzene is this or benzene is that. What is benzene? Because I said that the same molecule is expressed in the different form. So as that is the same molecule, then what is the meaning of these various forms? These various forms are resonating structures, canonical structures, and also called contributing structures. Also called contributing structures. We also say contributing structures. This looks more meaningful. Contributing structures means for one molecule. When you write here the various arrangements of electrons, various resonating structures or canonical structures or contributing structures, it means these various arrangements contribute their own properties to the actual molecule. That's why we say contributing one. None of the arrangement is complete in itself. None. This is one of the contributing structures, so this is not complete in itself. This is another canonical structure, this is not complete in itself. Benzene is neither this nor that. Benzene is something different of this kind, which is having properties of this structure also and that structure also. Like that, when one molecule shows resonance, means many canonical structures what will be there, all those canonical structures are contributing structures and none is having individuality. Any of the canonical structure cannot be considered that molecule. All are incomplete. There we choose one of the structure to represent that molecule. This is a different thing. We write this one, we say this is a benzene. Okay, you say benzene, there is no much problem, but you should not understand this only is benzene. This represents benzene. Benzene is something else. Then you will ask me, with this statement you are getting more and more confused. आप क्या बात कर रहे सर? Yes, what I say that as per this structure, let's mark these carbonatoms 1, 2, 3, 4, 5 and 6. 1, 2, 3, 4, 5 and 6. This structure suggests, you check this right now. I think it is audible. Harsha, have you joined recently? Who joined after the break? They will find their system by default in the mute. By default, that will be in mute. So what you should do, first you should check that one, you should unmute that one. Still if you are getting problem, you should refresh that one, you will be getting. Okay. I have here the two system. One where I can see the chat box in the videos, and other one where the live is going on. Okay, fine. So what I want to tell you, when you say this is the benzene, don't misunderstand. In this structure, there is double bond in between the C1 and C2, and there is single bond in between C2 and C3. When the single bond is there, then the single bond character will be there. When double bond is there, double bond character will be there. But in the actual benzene, there is no single bond character, there is no double bond character. Then how it is benzene? You write this structure. It is one of the best canonical structure. It is so good looking benzene kind of structure. We understand this only is the benzene. Actually this is not benzene, this represents benzene. Actual benzene will be something different. Actual benzene we write like this. Honestly speaking, actual benzene cannot be written, but it represents actual benzene. It does not represent actual benzene. We write. This is not the correct representation of the benzene. This is also not. This is. This is called canonical structure. That is called canonical structure, and this is called resonance hybrid. This is called resonance hybrid. So the actual structure, actual molecule which is having resonance is expressed by resonance hybrid only, and none of the canonical structure represent the entire molecule, the complete molecule. Canonical structures are contributing structures, contribute its properties to the actual molecule as per stability. The canonical structure which is more stable, that contributes more. The canonical structure which is less stable, that contributes less. Here I will tell you one what is canonical structure that I would like to tell you. Suppose I am taking class, physical class, you understand, not physical chemistry class. Okay. So when I take your class, one of the parent is coming and just saying to me, ki sir, you are simply sitting in the chair and keep on dictating the things, and you are not taking care of all the things. So I am very upset, and I have to give some evidence that no, I am not doing like this. So what I do, I bring one camera and I am giving one fellow and say that okay, you do one thing, that you take some random pictures. So he is taking some of the pictures when I am taking the class. In one photograph, I am there with just beside one fellow, in another one just beside another fellow, third one, fourth one, fifth